Okay, now, as we have discussed in the last class of this VLSI, that how basically we can obtain in the first step from the basic raw material our metallurgical grade silicon, and from the metallurgical grade silicon the electronic grade silicon. This is what we have discussed in the last lecture, that how can we obtain MGS and then EGS from MGS from the raw material. Now the next step, as we have said, that we have to discuss that how can we obtain the crystal silicon ingot. Basically, widely known methods are CZ or FZ method. That means Czochralski or float zone methods. So that we will discuss now. So what we have right now, we have purified of form of silicon, that means EGS with us, and this purified form of silicon is 99.9999999% pure, and it is in polycrystalline form. It is basically polycrystalline structure of silicon. And what we need single crystal structure of silicon. Single crystal structure of silicon. And that is what we obtain in this ingot. Okay, so this ingot we have to obtain from this basic raw material. That means this is not the raw material. From raw material we have obtained this EGS, and from this EGS now we will see that how will we obtain this silicon ingot, crystal silicon ingot formation. As already told, there are two widely known methods, that means CZ method or FZ method. CZ refers to Czochralski method and FZ method to float zone method. First we will discuss the Czochralski method. Let us have a look on this diagram. There are two things. In the left side you can see this Czochralski puller. Czochralski puller, as the name is indicating, puller. Actually, if you see here, this one, this is your puller mechanism. Puller mechanism means basically it pulls upward. It pull upwards. Okay, that is why this is known as Czochralski puller. And if you see this structure in this diagram, you see that there is a room. There is a room, and this machine is here at the bottom side. And vertically, you can see that it is touching to the height of the room. So if you see this puller mechanism, it is much lengthy. This is what I am telling you, so that you can visualize that the ingot which we are going to form is not of size like this pen which is in my hand right now. This is much bigger. This is of the size of length of near about our room length in which you are right now. I will tell you the dimension after a few minutes. Let us have a look onto the second diagram. Here you can see in this puller mechanism, this is basically the interior furnace zone, and this is your puller mechanism zone. Okay, here argon inlet, cable, seed chuck, camera, what are all these things, what is the purpose, that will be clear to you after few minutes. Okay, isolation valve, visor, optical pyrometer, vacuum pump, and water cooled jacket for this crucible furnace. Okay, so as I said, there are two main portions you can see here, that it is your crucible inside the furnace, and this is your puller mechanism. Okay, which is pulling this silicon ingot continuously upwards as it is forming. So first of all, have an understanding about that what basically is the size of this apparatus, what is basically the length and width of the silicon ingot which you will form. So as taken from one book, standard book, you can see as written, Czochralski Crystal Growth apparatus, also called as puller. One picture, this weighs about 17,600 kilogram, this much heavy weight, and 6.5 meter tall. Uh, it can we configure to hold a melt charge of 60 kilogram of silicon. 60 kilogram of silicon. So basically you can see here that which can be transformed into a crystal of 100 millimeter diameter and 3 meter length. So if I say that we are obtaining an ingot of cylindrical shape, as you have seen in the last diagrams, right? Then this is having a diameter of 100 millimeter. 100 millimeter is not big enough, right? 10 centimeter only the shape of this pen, right? But the length is 3 meter. That means near about 10 feet, right? More than 10 feet. So 3 meter is near about the length of your standard room, right? So this much big, not this much lengthy, right, as this pen, but the length of this pen is giving you the width of that ingot. Actually this much is in width and length is huge enough, 3 meter. So this much bigger ingot you are obtaining, and then from that ingot you will cut it into the pieces and obtain circular disc of 100 millimeter dimension, that is known as wafers, onto which you will form your integrated circuit. Okay, so if you see the major parts of this furnace, the known as Czochralski furnace, and the system is known as Czochralski crystal growth process, and the mechanism this puller machine is known as Czochralski crystal growth apparatus or Czochralski puller. In this, we have four major sections. One is the furnace, which contains crucible, susceptor, and rotating mechanism. Now, what are these things? What is the purpose of these things will be clear to you, as I already said. Okay, first we are seeing that what are the components. So, first we can see that there are four major components, that is furnace, crystal pulling mechanism, ambient control, and control system. In the first, that is the furnace, basically we have crucible, susceptor. Susceptor is for crucible support, and rotation mechanism, heating element and power supply, and the chamber, of course, right? Crystal pulling mechanism contains the seed shaft. What is seed shaft? I will tell you. Or chain, rotation mechanism, and seed chuck. Then ambient control includes the control of gas source, flow control, purge tube, exhaust or vacuum system, and the control system, which controls everything with the help of microprocessor, sensors, and gives the output. So these are the major sections which are shown here in this diagram. Okay, so now see which section is placed at which location. Okay, so you see here seed shaft, lift, and rotation is provided at the top, and this basically, this tube is basically is the rotating mechanism which is rotating, and here at the end, see this one, this is your seed crystal, this is your seed, okay, material, and this seed material basically is connected with this seed shaft, lift, and this rotating mechanism which rotates in one direction. Okay, and it goes into the furnace. Now what is this portion? This is your crucible, the furnace section. This is your furnace chamber. Okay, then crucible is here inside this furnace, which holds the complete charge, the material, the silicon, that is means EGS is placed here, right? And at the high temperature it is in liquid state, that means since it is melted, right? Seed shaft and chuck is here, this is that, okay, which goes inside this furnace and touch this melt, this silicon material. Okay, susceptor is here to support this crucible. Okay, the heater is to provide heat so that this material can be melt, and insulation is provided. Then control system and supply is separately connected, right? Control system is connected with the supply, sensors and processors are connected, so that we can visualize, we can check, like for example sensor for diameter control is here to check that what is the diameter of this circular this wafer which we are obtaining. Okay, so this is connected here. So control system and power supplies are connected separately for this purpose, right? See here, crucible rotation and lift. Here it was seed shaft and lift rotation, and it is crucible rotation and lift. So from the top, seed shaft and lift is moving in one direction, and from the bottom side, crucible is rotating in opposite direction. Okay, and vacuum is provided through this vacuum pump. Okay, so this is just the schematic representation of crystal grower. Now let us have a look on this video, which I have taken from the website, which is the link is written here in front of you. I have taken this video from here, and this is very good video which shows in itself the Czochralski crystal growth process in a much better manner. Now let us have a look on this video. As we have already seen the structure, you can visualize that structure. That this is basically, let us first see this picture, that this is basically the crucible, and inside crucible basically the material is in melting state, and outside crucible there is basically the support, crucible support is there, right? And the seed crystal comes inside this and touches it, and it is rotating in one direction, and crucible is rotating in another direction. Then when they will touch with each other, as shown here in this diagram, uh, see this one, when they touch each other, what will happen? This silicon will start combining with this seed crystal, and when we will pull this seed crystal upwards, what will happen? It will take away some silicon material out of the furnace with it, and when it will come outside, since it is moving in one direction and it is crucible moving in another direction, we will get a circular shape upwards, cylindrical shape upwards, right? So this thing will be more clear to you with the help of this video. Let us have a look on this video, how basically this process is going on. First of all, you can see the information from who has made this video. Now see, I have paused this. Okay, I am playing it again. See, from the top, in the starting you will see that from the top the seed crystal is coming downwards initially. Okay, and see this one. See, I am just stopping, and I am just pausing it, and it gets stopped. Okay, I will not pause it again. So you will see it now that the seed crystal is moving downwards toward the furnace. See, it is moving downwards towards the furnace. Inside the furnace, when it will touch, it will make contact, and when we will pull it out, it will take. We will slowly pull it out so that it will take some material with it. And when we are moving it and furnace in opposite direction, see, the crystal is coming out in cylindrical form, and it is obviously 99.999% pure. And when we are moving it at a fixed rotation speed, okay, we are getting single crystal silicon structure automatically, and we can have the wafer size as written, as you have seen, 4 to 12 inch. And this process is not so fast. See, takes up to 48 hours to complete. Takes too much of time. We will start it today, it will finish tomorrow, or maybe later. It is slowly it is moving, and slowly the material which is coming out is taking cylindrical shape and the single crystal shape. Okay, and you can see that here inside this furnace. See, inside this furnace what is happening? The seed crystal is touching, see the joint, and now it is moving, so circular shape is coming. And now when we will pull it out, see, it is rotating, circular shape it is forming, cylindrical shape, and when we will move, take it out, see, this much big cylindrical structure we will got, known as angle crystal silicon ingot. Then the next process steps are that we will cut it with the help of saw. Right, wafers are being sliced using a diamond encrusted saw, and then we will cut it. We will get circular shape wafers. We will pull out wafers is removed by a robotic arm and placed in a wafer carried board ready for polishing. Okay, this is what the process is. So I hope this Czochralski process will be clear to you now. uh, coming back to this diagram, see here that the seed crystal and single crystal silicon when quartz crucible inside the quartz crucible, that when this seed crystal comes, makes contact with the silicon molten state material, and when we will move it out because of the rotation in opposite sides, what will happen? There will be two actions taking place. We are moving crucible, we are rotating crucible in, let us say, in clockwise direction, anti-clockwise direction, and we are moving the polar mechanism in clockwise direction, let us say, because we are moving both in opposite direction. So what basically happens, centrifugal and centripetal force, the forces apply, and forces apply in such a manner that impurities move from the center to the outward side. That is how basically we get 99.9999% pure, that if any impurity is still there inside the furnace in the molten state material, because of this force which is appearing because of the movement in opposite direction, that will pull out the material from the center of the furnace towards the corners of the furnace. And when you are moving it, it is getting circular shape, single crystal shape, and you are pulling it out. At that time, single crystal shape structure in God will come out, and impurities will be moved away. Okay, rest thing already clear, will already be clear to you now, as I have already told you. Okay, so heat shield, carbon heater, purified crucible, crucible support, spill tray, electrode, what is the role, you can understand it now. One point to be noted is silicon is purified from basic raw material by refining, distillation, and CVD, what we have already done. It now it contains 1 part per billion impurities. Okay. All silicon wafers generally come from this method, which is known as Czochralski method. Another method is which is also widely used, is known as float zone method, that we will discuss in few minutes. Okay, polysilicon, you should remember this point, that is melted just below 1400 degrees centigrade. So silicon melting point is more than 1400 degrees centigrade. That is why the crucible, the furnace must have temperature in this range. Okay, and you should keep in your mind that pull rate, melt temperature, and rotation rate control the growth of the process. But basically, it means that how you are pulling. If you are pulling so fast, what will happen? It will not be able to take proper crystalline structure form. If you are moving it too slowly, what will happen? Some material may remain there inside the furnace, it will not be pulled out. Right? Similarly, temperature matters. If it is less than 1400 degrees centigrade, nothing will happen. And if it is much more higher temperature, then impurities will add on. So we have to think about the temperature also. Rotation rate control. See how you are rotating this seed crystal in, let us say, clockwise direction, and crucible in anti-clockwise direction. So rotation rate controls the growth. How? That if you rotate it fast, what will happen? The more the will be the speed, the more will be the diameter you will obtain when you will extract, pull it out according to the speed, right? So it will control the growth rate, will control the diameter, it will control the impurity and the structure, right? I hope this is clear to you now. So you have already seen this, that this is what the silicon ingot, which is finally gone, and then we can take it out from this puller mechanism. We can open the puller mechanism and we can cut the above upper portion seed crystal, and we can take it out for further processing. That means for slicing it and forming the silicon wafers. Okay, so this is Czochralski Crystal process, which is telling us that how basically single crystal structure can be obtained from multi-crystalline, that means polycrystalline EGS. Another method which we may also use is known as float zone method. Now, before proceeding this, I want to tell you that what is the difference in CZ and FZ method. First thing is that CZ method is widely used because it is costly but less costly in comparison to float zone method. Okay, that is why it is widely used. Both are used for the purpose of obtaining single crystal structure. Both are used for the purpose of obtaining single crystal structure from polycrystalline structure, right, from EGS. But if we compare the two, we can say that CZ method is less costly. That is why it is widely used. Then what is the advancement in FZ? Why we should use FZ? If CZ is less costly, we should prefer that. FZ will be preferred in the case when we need highly purified form. Highly purified form. So it can purify in a much better manner. Impurities will be no more. Okay, but it will increase the cost of the system and hence the cost of your IC. So in case if you cannot compromise with the impurities, you should prefer FZ. Otherwise, it is better to prefer CZ. And CZ in itself is sufficient for most of the process. That is why CZ is widely used. Otherwise, FZ is used. Okay. So let us see now what is float zone process. Alternative process of CZ is FZ, which can be used for refining or single crystal growth. See the structure. At the top side, it is polysilicon ingot. RF coil is in middle and single crystal silicon at the end. What is this diagram showing us? That actually RF coil is there, which is passed through this polycrystalline rod, and when it is passed through this polycrystalline rod, it converted into single crystal structure. Interesting? Let us say this is your polycrystalline rod. You have obtained. You create a RF zone like this. I say it is RF coil. When RF coil moves from up to down or down to up, what will happen? It will melt it and it will move further, move further. It will remove the impurity and it will convert its shape from polycrystalline to single crystal. It will move slowly and it will convert its shape from polycrystalline to single crystal and removes the impurity. How much simple is this? It looks like that, right? So let's have a look onto the picture which can explain this point in a better manner. Float zone crystal growth. See, once again the rotation here is in this direction and rotation here is in another direction. And why we do rotation in opposite directions is should now be clear to you. Okay, the gas inlet, the inert gas is used in the medium. Okay, and a chuck is there to attach the polycrystalline rod. This is your polycrystalline rod, right? Now see, traveling RF coil. This rounded structure is your traveling RF coil, which is traveling from upper to lower and lower to upper side, top to bottom or maybe bottom to top. I will tell you which direction. Okay, and the seed crystal is connected here. And see the molten zone. Inert gas will come out from this. Now, how basically this process is taking place? We start from the seed crystal, right? We start from the seed crystal. So, basically, what is happening? Let's say this is our rod. I am drawing it here separately. Okay, this is the bottom side and this is the top side. What is happening that initially we start from the top side. That means this coil structure is initially at the top side, right? So what happens that due to this traveling RF coil, wherever it will be, at that point where this coil will be, that material of that state will be melted. Okay, and the material of this region, which is actually this complete rod is basically in solid form. Okay, so this area will be melted, which is in contact with this RF coil. And when this area melted a bit, okay, not completely, the property, the interesting property is that the from heated area impurity moves away. And because of this interesting feature, what happens that impurities will move away downwards. Okay, now what will happen? Now in the next stage we will move the position of this coil. Okay, so we will move the position of this coil means, let me draw this diagram again to make the picture more clear. Now from this position we are moving coil to this portion. Okay, so what will happen, the material which was melted initially at the top side, right, at the top side, the material which was melted initially, this area will become solidify again. And now when it is solidified, you have seen that impurities have already shifted from it to the bottom side. Since the impurities have been shifted to this side, this area gets solidified again, but without impurity, and obtain with this rotation system it will obtain this single crystal structure. How? That I have already explained it to you, right, in the previous. So this is how basically we are doing that. What we are doing now, this is here in this zone. So what will happen in this zone, the area where the RF coil is there, this area will be melted. And since it is in melting state, what will happen, impurities will move away from this to downwards, and impurities will move downwards. And since we are rotating it in opposite direction, what will happen, it melted state, when it will be rotated, it will take properly the shape of single crystal structure wherever this melted state is there, right? And impurities will move continuously downwards. So slowly what will happen, all the impurities will come at the bottom side at last, and the from top to bottom side everything will be uniform properly in cylindrical single crystal structure form. I hope this is clear. Okay, so repeating my words once again, what we are doing, see, we are rotating in one direction here and rotating in opposite direction here, the crystal, the polysilicon rod and the chuck, and traveling RF coil is here. Basically what we are doing is that when we are starting from the top side of this polycrystalline rod, and when it is moving, the RF coil is moving such that from the top side, when it is there, it will melt the material and impurities will move downwards. Then RF coil will move downwards, so impurities will move again downwards, and so on the process will take place. And with its rotation in circular direction, it will obtain the shape circular shape, the cylindrical shape and the single crystal structure, and continuously in moving downwards, at last finally all the impurities will be collected at the bottom side. Okay, this is how this floating zone, the name is floating zone because wherever the RF coil is there, that zone becomes float. That is basically a floating zone, obviously, right? So the floating zone from top to bottom, and hence refining, the impurities are collecting at the last at the bottom side, right? So this is about the float zone crystal growth process. So now we have seen that we can say that in the first stage we have seen that how basically we can obtain MGS or EGS, that means polycrystalline polycrystalline silicon. That is what we have seen in the stage 1, right? Then stage 2 we have done today in this lecture. In stage 2, we started with this polycrystalline silicon, we started with this polysilicon, and we converted it into single crystal silicon. We converted it into single crystal silicon, right? using CZ or FZ method. This is what we did it right now. And now the next stage, that is stage 3. What is that? Stage 3 is silicon shaping. Silicon shaping means now we have this silicon ingot, cylindrical shape, and we will cut it and we will make slices. That means circular disc known as wafer. So the next step is silicon shaping, in which you will study that how basically wafer is prepared. That means wafer preparation. Okay, this is what we will discuss in the next lecture.